Okay, Assalamu alaikum everyone. Today, inshallah, hopefully this is the last lecture within this chapter. So in the previous two lectures, we have already covered the sun positions. In the previous lecture, we talked mainly about 2 points. The first one was solar time, and we know that, and we knew that we have difference between our clock noon or our clock time and the solar noon. And it is important for us to know the solar time because mainly it will define, or it will define exactly the time or the angular motion of the sun in the sky. So this one depends, or the difference depend on two main points. The first one is the length of the day, which we call it time correction, and the other one is your zone, which we call it longitude correction. So when we find these 2 points, longitude corrections and the time correction, and we add it to the local time, we can find exactly the solar time. The importance of solar time, because we care about more about the solar noon, where the maximum solar radiation we can obtain. And so if we determine exactly the solar noon, we can find the amount of solar radiation at this time, before and after this time. Also in the solar time, in the equation, there is a part which call it the day saving, and it's always between 0 to 60 minutes, so within 1 hour, and we know how to use this, or what is the purpose of the day saving. The other topic we talk about it was the solar angle, and mainly we covered two angles, which is the solar altitude and the solar azimuth. And to find this those two angles, altitude and azimuth, we knew both of them are function on the declinations, our angles, and the latitude or the positions of the country. Okay. It's very important, or the position of the sun can be mainly defined by these two angles. So if I know the altitude and know the azimuth, I can know the path or the position exactly of the sun within the sky. Today also we left with mainly two things. The first one, if you want to know the exact time for the sunrise and the sunset, and the day length, exactly the day length according to the motion of the sun. We know that always we say the sunrise or sunset defined mainly when I don't have or the altitude equal to 0. So how we define the sunrise? We will go to the solar altitude equations. Sunrise, I don't have altitude, so 0 equal or alpha equals 0. Sunrise also, the angle of the altitude equals 0. So if I substitute the value of the altitude here equal to 0, then I find that the sunrise is function in two things, or the sunrise or sunset is function mainly in the declinations and in the latitude. So rearranging this equation, we put this one equal 0, and rearrange this equation, we find that the H here represent the sunset. So now just arranging this equation as here 0, sine L, sine delta plus cosine L, cosine delta, HSS. HSS here denotes or refer to the sunset time. So rearranging this equation, we find that the sunset time equal to the latitude, tangent latitude, and tangent of the declination. As you see here, sine L over cosine L, which will equal to tan. Sine L over cosine L here, it's equal to the tangent. Okay, so HSS here represent the sunset time. Sunset time, exactly the time when I have the sun already going to be set. I don't have sun here. So that's mean we don't have sun radiation, 0 sun radiation, since I don't have it's sunset. Sunset time here, it's represented, HSS represented as an angle, 0. with angle, I mean degree. If I wanted to be represented in terms of hours, remember that we said that the solar noon at 0 degree. When we talk about the imaginary lines that the surface or the Earth divided to it, and we said to move from one longitude to another, we need 4 minutes. That means we need 1 hour to cross 15 longitude. So HSS here, which is the sunset time in terms of hours, in hours times, the same equation here, minus tan L, tan delta divided by 15. So 15 here to convert degree to hour time. Okay, so HSS represent the sunset time. The sunrise time here is before the noon. So here the sunrise, that's mean equal to the 12, which is solar noon at 12 minus the sunset. So if I find the sunset, take from it 12 or 12 minus sunset, I will find the sunrise. The third one is the day length. Always the day length is twice the sunset. So if I find only the sunset, I can find from it the sunrise and the length of the day. This is exactly the time according to the motion of the sun within the sky or in the sky. Okay, so I have here, adding to the previous equations, which was for the latitude and azimuth, how to find the sunset and the sunrise time and the length of the day. The last angle also we can talk about it is the incident angle. Always we care to or we want to have maximum radiation incident on the collector. Okay, so this angle, which we defined as the incident angle, represent the angle between the sun ray, this is the sun ray, and normal to the surface. That means if I have, this is my surface, say if it's horizontal, and here is the sun. Okay, so this is the sun ray, and if suppose this is the line horizontal or normal to the surface, so this angle represent theta, the incident angle. If my surface, this surface is tilted, for example like this, so here I have angle tilted. Oh, sorry, I'll just make it better. If this is my surface and it is tilted with an angle beta, such as this surface here, tilted with an angle beta, and here is the sun, so this is the radiation from the sun, this is the sun, so this is the beam or total radiation incident from the sun. This angle, which is between the sun and normal to the surface, represent the incident angle theta. Okay, so we always care about the incident angle, because depending on the incident angle, I'm going to capture more solar radiations. So what is the incident angle and what is function on? The incident angle, as we define now, it is the angle between the sun ray and normal to the surface. So this long equation represents the incident angle. As you see, its function on your location, so latitude, on the declinations, on the hour angle. We have another two important angles related to the surface, which is the surface, the tilted angle beta, and the surface azimuth angle ZS. So here the incident angle is function on the latitude, on the declination, on the hour angle, and on the beta, which is the surface, which is the tilted angle, and on the surface azimuth angle. Take care, I said surface azimuth angle. We have two azimuth angle, one related to the sun before we talk about it, Z, and now I'm talking about the surface azimuth angle related to the surface. Both of them are due to the south, towards the south, or from the true south. Okay, this incident angle, these long equations have special cases depending on my collector. So the special cases, number one, I said two angles from this equation related to the collector. The first one, tilted angle. The second, surface azimuth angle. So if my surface, this is the surface, is horizontal, this is the surface is totally horizontal, which angle will be equal to 0? So imagine this surface is horizontal. That means I have horizontal surface. I don't have my tilted angle equal, I have tilted angle, as you said. Done, yes. So I have beta here, which is the tilted angle equal to 0. So in this case, tilted angle beta equal to 0. I will go to the equation here, this long equations, and substitute beta with 0. I will summarize this equation into, I will take the first part here, we will find it. The second part will be cancelled since I have sine beta. The third part, it will still there because I have cosine beta, which is equal to 1. The fourth part will be cancelled, and also the fifth part. So here, for horizontal surface, when that means the surface will be horizontal, I don't have tilted angle, beta will be equal to 0. So the incident angle here function only on the other angles, which is the latitude, the declinations, and the hour angle. It's not going to be affected by the azimuth surface angle and the tilted angle. Okay, so this is the incident angle cosine theta. The other case, if I'm going to put my surface to be totally vertical. Totally vertical. So the other angle here also beta. So in this case, we will have the beta or the tilted angle equal to 90. The same here, some of this part will be equal to 0. So the first part here, I think, is equal to 0. The second part will be there. The third part also equal to 0. So here, the surface or the incident angle will include the azimuth surface angle. So it will be function on latitude, on the declination, as well as in the surface azimuth angle. If it's only horizontal, so the surface azimuth angle has no influence on the incident angle. If it's vertical, the surface azimuth angle will have influence on the incident angle. Another two cases also related to the surface, which is the first one, if my surface facing the south or the north. So if it's facing the south, we know that which one is important here. It is the surface azimuth angle, ZS. So the incident angle will be reduced to these equations. Okay, we'll have, it will be function also in latitude, beta or tilted angle, and hour angle. If my surface facing the north, so in this case, the azimuth angle, surface azimuth angle will equal to 180, and this is the special case for it. So the general equations for the incident angle, as we see here, this is the general equation for the incident angle, is function in many parameters or many angles, but we have 4 special cases from it. This incident angle related to what? To the fixed surface. That means I have my collector fixed. So I'm going to fix the incident angle, or this is the angle I care about. So this is related to the fixed surface. If I have moving surface, then the incident angle will be will take another view. We'll see later. But before here, we always trying to obtain maximum radiations, which means that we always try to obtain the optimum slope of the surface or optimum tilted angle. Always, you know, or always in your work, you try to obtain the optimum. You know that it is the beta or the tilted angle. You make it equal to the latitude. This is for the whole year. However, if you can't change the position or the tilted angle of your collector, so it is better for the winter to be more vertical. So the rule of thumb to obtain more solar radiation, to make your solar collector should be more vertical during the winter. If you see here, this is the winter. In the winter here, you know, you find it is, I may have first, it's short day, as you see, as well as the sun radiation or the radiation here, it has low. Okay, short day, low sun radiation. So if I make my collector more vertical in winter, I will obtain more radiation. Opposite in the summer, we try to make more tilted for the solar in the summer to maximize the output. Okay, so beta or the tilted angle is function on the latitude, the position, and declinations. So always we make it equal to the declination. Just if we make it fixed the solar collector. Up to here, is it clear? So let's go. So this is example. We want to find the solar altitude, solar azimuth angle at 2 hours after local noon. So we're going to use this number 2 hours after local noon to find the hour angle H. After local noon, that's mean BM. So 102 hours, so 120 minutes. So which sign will take? BM, it will be positive or negative? BM, it will be positive. Yes, it will be positive, Sultan. So as I said here, we'll take positive. On June 15, so this is the number of the day on the year. We'll go to the table. We find it before, and we find which day exactly 15 June. It's equal in the day, so we'll see the accumulation of the days before it, and you find which day exactly. Okay, so this is the day, and we need the day to find the declination, because declination only function on the day for a city located at 40 north latitude. So this is the L locations. Also find the sunset and the sunrise hours and the day length. This is all the things that already we covered before. First thing, the solar altitude. This is the equation for solar altitude. Since I have a time, it's not at the noon, so I'm going to use the general equation. If it was at noon, this I can minimize this equation and use the normal altitude, which it's alpha n equal 90, and the other equation 90 minus delta and latitude. So here we're going to use the general equation, altitude, alpha altitude, L is equal to what? Equal to 40, we have it. Delta, please can you calculate delta? How much is equal? N first, what is N? What N in the year? You have the table. What is the number of N in the year? 166. Okay, so you find delta here for 166. Then H, how much H is equal? 14.9. This is what 14.9. Delta. Okay, I'm not sure actually. Is it 14.9? So he said 14.9. You just check. I don't think it's 14.9. Just check, yeah, Adnan. Yeah, it's 23 something. I don't think it's 14. So check it, Adnan. It's 23 point something. Okay, so delta, it will be 23 something. I'm not sure how much is exactly, but 23 is not 14. So this is the first one. So this is delta. Yes, Saud, all of them, they found it 23.31. And alpha, so you find delta. Our angle, how much? Adnan, you can say our angle. H equal to what? Adnan? Adnan, you are with us? H equal to? Okay, Omar? Yes, Adnan, 30, thank you. It is equal to 30. Since it is 2 hours, 120 times 0, and it is positive because it is BM. So I have H, I have delta, I have the latitude. Alpha equal to what, ya Omar? Omar Adil? Alpha. I got it 49. What is 49 so is it? Actually, the alpha, is it 49? No, Mustafa, it's impossible. 300. Yes, 73 alpha. I'm not sure. Just check, both of you. It's not like this. So just we're going to substitute in this equation and we find alpha. Okay. After alpha, we have azimuth angle. So another volunteer, what is the azimuth angle? Make a calculation for it, please, and find the value of azimuth angle. I'll just see the names. Pick any name. Ali Umran. Badr. Okay, Tamara, you find it 65, thank you. Badr, you can find for us the sunset time. Sunset time. Hissa. Omar, alpha is 59. Maybe it's near to that number, yeah. Hissa, 7.4, this is the sun set time, yeah. So can you convert the sunset time? This is by decimal. Can you convert it to hour and minutes? How much exactly? 7.4 or 7.6? No, 7.4, as you said. How much exactly this time? يا حصة 7.24. So it's the hour 7 morning is 7 hours and 24 minutes. Okay, so now we know the sunset. The sunrise will be equal to 12 minus 7.4. As Amna said, it will be 7.4. Also, if you change it to if you have to change it to hour and minute, so it will be almost 7 or 4.36. Okay, the length of the day is the multiply the sunset time time 2. Okay, is it clear for the all? Okay, thank you. So the solution already here. You can find it. Just I want you to follow the steps because of that. So here is the solar altitude. This is the sun set 7.4. How to convert it? You know how to convert from the decimal to hour and minutes. and here is the sunrise 12 minus the sunset. So you convert it also solar azimuth, and the day of the length, it is the sunset time 2. Okay, طيب. This is also example for the incident angle. We have this. I want you to tell me each one represent what. A surface tilted 45. So 45 represent better beta. Okay. From horizontal and pointed 10 west due to south. When you see the word due to south, so this represent azimuth, surface azimuth. Take care. It is not solar azimuth. The difference between solar azimuth and surface, as some I'm taking here about the surface. So this is ZS only. Okay. Is located at 35 latitude. So this is L. Calculate the incident angle at 2h, 2 hours after local noon. So this is positive 120. From here we can find the hour angle. Local noon on 15 of June. So this is the day we can find that declination. Just we substitute all this value and we find the incident angle. Okay. This equation, as I said, the incident angle is for the surface, fixed surface. But what if I have moving surface? We always try to find maximum solar radiations, and we're making tracking system to make the surface tracking the sun. For the tracking system, we have either can be classified according to the mode of motion. That's mean I have full tracking, which we call it 2-axis system, or we have single axis system. So either I have full tracking, which we call it 2-axis system, so the surface will move at 2 axes and try to follow the sun. The second is the single axis, and this single axis, the surface will track within 1 axis. This axis either it will track from east, the surface will track the sun from east to west, like this, from east to west, and the surface, the axis of the surface from north to south, and the tracking from the east to the west, or the surface will track the sun from the south or north to the east. This is 2 axis, this is the second position, or the surface, we will make the surface tracking the sun, okay, from east to west. However, the surface axis will be located to be parallel to the axis of the air, or we call it polar axis. What is polar axis? Polar axis is the axis that connecting the north, it is actually imaginary line drawn from the North Pole to the South Pole, passing through the center of the Earth. So here, this is the red line here. This one is moving from the North Pole here to the South Pole, moving or passing through the center of the Earth. So I will put my collector. This is the collector, or this is the surface. Okay, the axis of the collector parallel to the axis of the Earth, or to the line of the Earth. Each one of these arrangement will have different incident angle. Each of these arrangement will have different of incident angle. For example, or we start by the first one, which is the full tracking surface. So for the full tracking surface here, I'm going to make the system track the sun in 2 axes. So I'm not going to fix the incident angle, will be theta, which is the incident angle equal to 0. Equal to 0. So I'm going to maximize the cosine theta. Cosine, whenever I'm maximizing the cosine theta, I will obtain more solar radiation. Whenever I'm maximizing the cosine theta, I will obtain maximum radiation. So here cosine 0 equal 1, which is the optimum. So what happened for the surface? How it can follow the sun? I will make the angles of the surface is almost equal to the angle of the sun. I will try to make the angles of the surface equal to the angles of the sun. Type which angle of the surface we have it? As you see previous, the incident angle, we have tilted angle or the slope, and we have the solar azimuth angle. I have the slope and I have the surface as a surface azimuth angle. These two angles are related to the surface. So for the slope or the collector tilted angle, I will make it equal to the solar zenith. So here we have beta, which is the tilted angle, equal to the zenith, which was phi, if you remember. Okay, the other angle is what? Is the surface azimuth angle, which is ZS for the surface, equal to the sun surface or to the solar azimuth angle, which equal to the Z. This is full tracking. Here, in this case, the collector will track the sun, and it will obtain, or it will have maximum solar radiations. The performance of the full tracking system with respect to this angle during the day is shown here in this figure. So if you see, if I'm making the collector following the sun, obviously will be almost we have the maximum radiation at summer. So here at summer solstice, this one here will be the maximum radiation. Then at equinox, as you've seen this, the second graph, and the third one here, the equinox, whatever. So I will just make it bigger. This one here, it shows the daily variation of solar flux for full tracking system. You will find, and always the full tracking system is the maximum we can obtain from it. So always we try to maximize cosine theta. Maximize cosine theta, that means theta equal to 0 in this case, okay? And the angle of the surface will be equal to the angle of the sun. This is the output. As you've seen here, this the first one here is for summer solstice, the maximum output. Then for equinox here will be second one, and the third for winter solstice. If I change, instead of using, this is the full tracking already, we find it. The other one, as we said, we have the single tracking. So single tracking depend what is the position of theta, or what is theta equal, depend on the axis. The first one we have said for the single tracking, I have three classification. The first one, if we make the axis of the collector parallel to the polar axis, and the tracking from east to the west, from east to the west. So in this case, the incident angle will equal to the declinations, since the surface will follow the earth. So the incident angle, it's better to make it equal to the declinations. So if you see, when you remember when we talk about the declinations here, we said the sun, the declination as we defined it, is regarding to the equatorial. And we said in the equinox, fall and spring, almost the sun is perpendicular to the equatorial. And then start to have declinations, positive in the summer and negative in the winter. So if I see the performance of the system. When it is, I'll make it more, this system, when it is at polar north axis, the tracking from east west for the polar axis, we find the maximum solar radiation obtained at equinox. It's not at the summer. If you remember here, we said perpendicular in the equator at the fall and the spring. So the maximum output will be at the equinox. Then we have in the summer, this is the second one as you've seen, and here the third one on the winter. The third case here, or the second case from the single axis, if I have my tracking system going from north to south, this is also the output. Okay, we find maximum at summer, then equinox, and minimum at winter. And in this case, if you see here, at winter we have very low radiations. In this case, if I have it, the tracking from north to south, I have very low solar radiation, and most probably due to the shadow towards the north. So always, if I have north-south tracking, expected to have low radiations, very low. Always we have low at summer, at winter. But in this case, it will be more low in the winter. In the opposite here, if we make it tracking from east-west, also single tracking, but from east-west here, we'll find here the winter is more better, the output from winter is more than the one that tracking from north to the south. So this is the 4, and this is the incident angle if I make this type of tracking. This is the 4 or the 3 types or the 3 equations in terms of single tracking. And here I have comparison between the output. I know that the full tracking is the maximum. So for equinox, for summer, for winter is the maximum. Then I will compare the other position. That's it. As I said, the polar, the north, horizontal or east-west tracking, and north-south tracking. We find that the full is the maximum. So comparing to full, the other one is the polar tracking. In this case, I will have, as we said, maximum at equinox, and summer I have almost 91%, less than the full, and the winter also I have maximum. For the east-west tracking, north-south, this is the surface of the axis. So here we will have maximum at summer and equinox, then in the winter it will be 60% and the other. So this is depend in my situation which one I'm going to use. Full tracking, sure, it will be the best. Then depend the other position I can have. I can find which one is better. Okay, 1 minute. Okay, sorry for disturbance. Okay, Omar.
Doctor, actually for the horizontal axis tracking, we have 2 types, which is the north-south and the east-west. Which one changes the surface azimuth and which one changes the tilt angle?
Which one? You mean which, if I go back, which slide here? You mean for the moving surface or the tracking one, yeah?
Yeah, the solar panel, like or the collector. When we move it, which one changes the tilt angle of the solar collector, and which one changes the surface azimuth?
Okay, if you make it for the full tracking here, you're going to follow. It will be the beta and the surface angle, both of them here. It will be changed for the full tracking. The beta and the azimuth angle. This is for full tracking. Okay?
Yes.
Okay. For the others here, if I'm talking about, this is for full tracking. If I'm talking here about the this one, this only will depend on the declinations. So you are going to put your collector axis towards the axis of the polar axis, and you care about the incident angle. So incident angle, what we defined it, it is the incident between the sun and normal to the surface. So when you put your collector towards the polar axis here, so what is the normal to it, and the difference between and the angle between the normal and the incident, this is will represent the theta. So theta here almost will be equal to the declination, whatever your beta, you mean the tilted angle. Beta tilted angle, try to make it for optimum always, but here it will be moving actually. Did I answer your questions?
My question was regarding the slide after it and the one after, which is the
This
horizontal one, east, west,
This
and
one.
north, south. Yeah.
Okay, so here you mean the incident angle for this one?
Yeah, I mean the two types of tracking, which is the horizontal. One changes the surface azimuth following the sun azimuth, and one changes actually the tilt angle of the collector based on the altitude. So which one changes the surface azimuth and which one changes the tilt angle?
This one is one is changing the surface azimuth and the other the tilted angle. For this one here, when you make it here, it's changed. Just let me see here. This is changing north out. This is changing the tilted angle. Okay, and here, because here is this one, the axis of your collector is from east to west. This is the axis of your collector. Okay, and this is the tracking from the south to the north, from the south to the north. So it will change now from south to the north. This will change the azimuth angle. This one will change the azimuth angle. So it's moving from the azimuth angle for the surface because it is from the south to the north. The other one here, the other one is changing the tilted angle if it's not horizontal. Is it clear?
I think this one changes the azimuth, the horizontal north-south with east-west tracking. This changes the azimuth because the one before it changes the tilt angle.
This one here, it's horizontal, yeah. This one is horizontal, so I don't have here tilted angle. It's already if it's horizontal, but if it's tilted, it will be like this, and this is beta, yeah. If it's tilted, so it will move like this, and it will move from east to west, from here to here. So which one is going to be? It will change the azimuth here.
Yeah, surface azimuth.
Yeah, because this is the beta. Is it? I'm right. Is it? I get into your questions.
Yeah. Thank you. I got it.
So this is the beta here. So this is the comparison between the four cases. Now we already talked about the angles, or the two important angles, as we said, is the altitude and the solar azimuth. Type. Usually, to use equations to finding the solar azimuth and altitude is not practical. To make it practical or more practical, we have which we call it the sun path diagram. So what is the sun path diagram? We know that the altitude and the azimuth is function on three main things, which is the latitude, the hour angle, and the declinations. Okay, so we have drawing the solar altitude and solar azimuth as a functions in the latitude. So I will have graphs for each latitude. Here the graph for latitude says 34. So each latitude, individual latitude, I will have graph for it, drawing the solar altitude, solar azimuth, and these lines, which is blind here, represent the declinations, and these dot lines represent the hour angle. So here, more clear here, this is the latitude. So depending on the latitude, I will have a graph, many graphs like this, depending on the latitude, 30, 40, 45, whatever. Each latitude will have the declinations, and this dots line represent the constant hours from the sunset to the sunrise, from the sunrise to the sunset, and here representing the noon. So if I want to know the altitude, simply I go to the day, say here, or the month, say this is for December, and I will check the hour also, go to find the solar altitude and solar azimuth. For example, here you can see this one more. This is the altitude. The altitude also is drawn at the solstice days, a certain day. For example, here, this is at 22 of December. Then I have January, 19 January. I have 21 February, 20 March, 20 April, 22 May, 22 June. I'll make it by pointer, starting again here. 22nd of January of December, 19 of January, 21st of February. I'll go up here, 20 of March, then here, 22nd of May, here 20 of April, 22nd of May, 22nd of June. Back again here and find 23rd of July, 23rd of August, 23rd of September, 23rd of October, and 22 of the November. This is the whole months within the year, the whole year and the months of it. And these lines, bigger, these lines here are dotted. It's here 7, 8, 9. So this is AM. Until here, say at the mid, it will be noon, 12. Then I will go 1 p.m. 1, 13, 14, or whatever, 13, 14, 15, which is 1 p.m., 2 p.m., 3 p.m. Okay. So if I have, for example, this one, polygon, here, for example, say that I want to find the maximum solar altitude, at say February, So here, this is represent 28 or 21 of February. So I will go directly. This is the maximum, and I will go here. The altitude will be this number, which is 40 something. And at noon, it will be here, which is the azimuth equal 0. Always the altitude will be maximum at the noon. We said that highest position of the sun at noon. If I have, say another example, I want to find the altitude, solar altitude, and solar azimuth for 21st of October, say at 10 a.m. So where is the October? This is 21st of October, this line. This is the 21st of October. At 10 a.m., this is the intersection of the hour, this is a.m. So intersection of 10 a.m. with the 21st of October, this point. And I will go horizontally. This value represent the altitude, and down here represent the solar azimuth. So if I have the graph, directly I can find the value of altitude and solar azimuth without going back to the equations. So it's make the life more easy. Okay. Also, if I have tracking system, say I have tracking system, and I want to find the optimum angles for this tracking system to capture the maximum solar radiations. If you remember when I said tracking system, I said for tracking system, the optimum angles to make full tracking, to make beta, which is the incident angle, equal to what? To the zenith angle, phi. And the surface azimuth angle, ZS, equal to the solar azimuth angle, Z. I want you to find these optimum angles using the sum path diagram. How can find it? How we can find these optimum angles using the sum path diagram, say for August 21 at 11 a.m. Okay, August 21 at 11 a.m. Any volunteers? I want to find the optimum angles, beta and ZS, which for the optimum angles for the full tracking system at 21st of August at 11 a.m. using this angle. I'm not going back to the equations. This chart, sorry. I'm not going back to the equations. Okay. As I said, beta will equal to the delta to phi. And I said 21st of August at 11 a.m. So this is the line for August. Do you see? I'll make it more bigger. You want? Okay, here. This is okay. This is the 21 of August at 11 a.m. here. Type. If I go to this side, altitude, Adnan, he said the altitude equal to 60, 60 something, say 65, for example. This is the altitude. And I will go down here, say 35 or whatever better, 35 is the Z. So I have phi alpha equal 60 or 65, for example, and I have Z for the sun equal, what we say, 35, say 35. But these are for the sun. I want for my surface, the optimum for the surface. Type, I want beta equal to phi. If you remember before, we know that alpha plus phi, yes, equal 90. So beta equal to 90 minus phi. And for the surface azimuth, it should be equal to the solar azimuth. So ZS equal to the same, which is 35. Okay. So using the diagram here will make it easy, and we can find the angles without referring to the equation. However, you should remember that each latitude have its own diagram. So when you start to use this diagram, you should know your latitude and choose the correct diagram. Okay. Any questions up to here? Okay. I will stop to this point. Minute. Next lecture, inshallah, we'll continue with just there is we have a theoretical part regarding the instrument that used for to measure the sun radiations, pyrometer and barometer. Just we're going to start talking about them. Then we'll start chapter 2. Okay. Before that, now I want to know, we have quiz next week, inshallah.